Welcome back to the Algebraic Graph Theory Seminar. This week we have Mike Tait, and he'll be talking about two conjectures on the spread of graphs.
Sorry, I'm going to reshare. I don't know how to unmute when I'm sharing. Okay, so you can see my screen right now? Okay. Yeah, so yeah, thanks for coming. I'm really happy to give this talk. I'll explain why shortly. But yeah, thank you for coming. So this is a talk in spectral graph theory and specifically with the adjacency matrix. This is the definition of the adjacency matrix. The only thing that I want to say about the adjacency matrix is that it has a real set of eigenvalues. So we'll order them like this. N is always going to be the number of vertices in the graph. And I'm basically in this talk going to be interested in how large this range is. And so to that end, we'll define this spread of a graph. You can define the spread of a matrix in general, but the spread of a graph will be the distance between its most extreme eigenvalues. So just lambda 1 minus lambda n. So that's the topic of this talk. And we want to sort of know what does this say about a graph. Just some general intuition about this. Lambda 1 is saying something about connectivity in the graph. It's saying something about density of the graph. So if you want a large lambda 1, that means you want there to be a lot of edges. You want there to be a lot of connectivity in your graph. And lambda n is saying something about bipartiteness of your graph, right? So lambda n is less than or equal to lambda 1 in absolute value, and you have equality if and only if the graph is bipartite. So this is something you learn very early in spectral graph theory. And so this lambda n is, it's telling you something about how bipartite your graph is. And so if you want to maximize this quantity, the spread, you sort of need your graph to be dense and you need your graph to be bipartite at the same time. And these two things sometimes are competing with each other. If you have more than half density, so if you have density so that the graph can't be bipartite anymore, then adding edges is sort of making your graph less bipartite in that situation. And so these things can compete. And so you can ask sort of how large can this quantity actually be? And that's the topic of a conjecture of Gregory, Hershkowitz, and Kirkland that I'll call the spread conjecture. So this first one is called the spread conjecture. And it says that if I want to maximize this quantity, the spread, over all n-vertex graphs, I should take the join of a clique on 2n/3 vertices and an independent set on n/3 vertices. So this graph is fairly dense and it has a large complete bipartite subgraph at the same time. And so you can kind of see that this is a good candidate to sort of try to be very dense and very bipartite at the same time. Okay, and so they made this first conjecture, the spread conjecture. And they made an additional conjecture, the second one, which I'll call the bipartite spread conjecture. And this says that if I fix the number of edges in my graph, and this number of edges is less than n²/4, then the graph that maximizes spread over all graphs with that many edges should be bipartite. This quantity is, it's an amount of edges where you can have a bipartite graph. Right. And so since the density is fixed, if you're fixing the number of edges, the density is fixed, and you're in a range where the graph can actually be bipartite, it's very natural to think that, well, I should just choose a bipartite graph then. And so that's the second conjecture. It seems almost trivially true. That's how I felt about it when I read this conjecture the first time. Okay, so some evidence for these conjectures comes from their original paper. For the first one, the extremal graph is a join. They showed that. So their conjecture is that it's the join of this clique and independent set. And they showed that whatever the extremal graph is, it's a join. So I'll explain more about this later. They showed that if you restrict to complete multipartite graphs, then this graph is the maximizer. They proved some bounds on the number of edges that the extremal graph has to have, and their conjectured extremal graph is in this range. And they showed that for any graph G, the spread is bounded by something like 1.2 times n. And their extremal graph has spread approximately 1.15 times n. So they proved an absolute upper bound, which is reasonably close to what they think the actual bound is. For the bipartite spread conjecture, they showed that the spread of any graph is bounded above by twice the square root of the number of edges. And if you take a complete bipartite graph, its spectral radius is square root of the number of edges, and lambda n is negative square root of the number of edges. And so if the number of edges is of the form where you can have a complete bipartite graph, then it's best possible by this theorem. And so, so it seems very natural to make this conjecture. And they tested all graphs up to 8 vertices for this bipartite spread conjecture. So before I say our results, these are my collaborators. Alex is Maria Aksanovic's postdoc now. John is finishing up at MIT and is going to be a postdoc at IAS next year. And Jane is faculty at Ontario Tech. And so the last couple of years, we've been working very hard on these problems, and it's been a lot of fun. Okay, so I'm very happy to say these theorems that for the first conjecture, the conjecture is true for all sufficiently large n. So for there's some constant n such that for all n larger than that, their conjecture is true. And furthermore, we can show an absolute upper bound for every n that looks like this 2n over square root 3. And so this is correct basically up to this 1 over square root 3 term. So that's true for every n. But the main thing is this solution for all n large enough. Okay, so the first conjecture is true, and the second conjecture, I'm going to rephrase it slightly. So let me say this notation. So SNE is the maximum over all graphs with E edges, and this S sub B NE is the maximum over bipartite graphs with E edges. And so the second conjecture, the bipartite spread conjecture, says that these two quantities are equal, right? And so our second theorem is we gave an upper bound for this difference between the two. So their conjecture says that this difference should be 0. And we gave an upper bound that looks like this. And this is a good upper bound if the graph is dense. So if the graph is dense, the spread is linear in n, right? And the number of edges to the 3/4, as long as the number of edges is more than something like n to the 3 halves, this error term is going to 0. But more surprisingly, their conjecture is actually false. So we showed that for any n large enough, there is a choice of E less than n squared over 4, so that the conjecture is actually not true in that case. The graph that maximizes spread in this case is actually not bipartite. So this conjecture that I said is very natural and seems almost trivially true. That's how I thought of it. It's actually false. So this was very surprising to me. Okay, so I want to say the story of these theorems. And the reason I'm so happy to give this talk is that this is the problem that I've been thinking about the longest in my life, actually. So I first learned of this problem, this right conjecture problem, 10 years ago when I was a student at Delaware. Sebi told me this, and I really liked this problem. I thought it was really interesting, a fun problem to think about. And so I thought about it like a lot, and every few months I would sit down and try to solve it. And I didn't make any progress. So I spent 5 years thinking about it and not having any good ideas, basically. And then after 5 years, I still didn't make any progress. But additionally, I started working in spectral graph theory more. So I was giving a lot of spectral graph theory talks. And I would mention this problem in every spectral graph theory talk that I gave. So I was like thinking about it every few months. I was asking everybody in spectral graph theory that I knew about it. And additionally, I was saying it as an open problem in all of these talks. And still, like, there were several more years where just nothing happened. In 2017, I was at the graduate research workshop in combinatorics with Alex and Jane. And at some point, I'm not sure if it was during that conference or during a later conference, we talked about whether using graph limits might be a good idea for this problem. I sort of had that thought over the years that potentially this might be a good idea. And then something happened. So in 2019, we made a small observation that basically gave us a foothold onto this problem. I'll explain what this breakthrough was. It was basically just an extension of something that was in the original paper, but it allowed us to have some idea of what was happening, and this sort of pushed us to think more about the problem. This picture, if you can see here, this says spread conjecture solved. This picture was taken in January of 2020. There was like a few hours where we thought that we had solved the conjecture, but we were really, really wrong then. There was a lot more work to do. Yeah, so there was about a year and a half more of work to do after this picture was taken. Soon after this picture was taken, like the next month, John came to give a colloquium. At this point, we had realized that we had not solved the conjecture, and we were trying to solve it, of course, and there were some optimization problems that were coming up over and over again. We were trying, and like we don't know very much about optimization, and John knows some stuff about optimization, so he came to give a colloquium and joined our project. And at this point, we found a counterexample actually to the bipartite spread conjecture. So that was sort of very surprising. We were trying to prove it, and there was like a step that seemed obvious, but we couldn't prove, and then that led to finding this counterexample. Okay, so since then we've been working very hard. Progress has been slow at times, but I'm really very happy to say that the theorem is completely proved now, and all that's left is writing now. And writing is taking a while, and it's because the proof is very long and involved. Okay, so there's a lot of steps that go into the proof. There's a lot of different techniques that we use. The paper is like 65 pages long, and so it's taking a little while to write. But that's where we are now, so it should come out soon. Of course, since the proof is so long, I'm not going to give you all the details in this talk, but I want to give you an outline of how it works, and I want to give you some details that give you some flavor of what's going on in this proof. Okay, so the outline is, the first thing is we had to extend some structural results from the original paper. So they proved several results about what the extremal graph should look like, and we needed to do an extension of those, basically. And then one of the backbones of the proof is something that's very, very common in extremal graph theory. And as I write more papers in extremal graph theory, I realize how often I use this idea from calculus that just you want your first year calculus students to understand, is that like, if you're trying to maximize a function, wherever the maximum is, like the derivative should be 0. Or what I want to say is that if you're at a maximum, if you move a little bit, you can't increase your function, right? So it tells you something about what the function looks like at that point. And the same idea is used actually a lot in extremal graph theory, that like if you have an extremal graph, well, if you alter this graph, your function can't increase. That's the idea. And so that tells you something about the structure. So you know you have your graph. If you move a little bit, your spread has to go down, and this gives restrictions on what the graph can look like. So we do that, and then we translate to graph limits. Okay, I'm not going to say a lot about graph limits in this talk. So we do this kind of averaging, and we show that there are actually only 7 kinds of vertices. So what I mean is that if there are more than 7 types of vertices, we can do some averaging and increase our spread, and that's a contradiction. And so what I'm saying is that like in the extremal graph, you can make a quotient matrix that is at most 7 by 7. And you can calculate the spread of this quotient matrix, and then that's the spread of the original graph. And that sounds pretty good. Like when we got to that point, I was sure that we were almost done. But it's surprisingly tricky. Like you don't know how many vertices there are of each type, and 7 is 7 is bigger than you think when you first hear it. So there's actually more that you have to do, and to finish the proof, we had to use something called interval arithmetic, and the proof is computer assisted at this point. So I'll explain a little bit more about that. And then there's some messy things that you have to do, and you have to translate back to graphs. Okay, so this is kind of the high level outline. I want to just make a remark about graphons that before this project, like I didn't know anything about graphons and I was a little bit scared of them. There's like integrals and stuff everywhere. And if you feel that way, that's fine. Don't be scared of this. There's using graphons is not why we were able to prove this theorem. You could rewrite all of our arguments without using any graphons at all. It would just be messier. So it just makes it cleaner, basically. And because of that, I'm not going to say anything about graphons in this talk. So you don't have to worry about that. But the only thing I do want to say is that because we're using this idea, when I say things, they might not apply to a small number of vertices. So when I say things, it only applies to like a linear size set of vertices. And then at the end, you have to deal with this small set of exceptional vertices, but you can do that. Okay, so I want to talk about some of the ideas. So the first step in this high level outline was to extend these structural results that were from the original paper. So let me say some ideas from the original paper. We're going to use this Rayleigh quotient constantly, like throughout the whole paper. The spectral radius is the maximum of the Rayleigh quotient. The smallest eigenvalue is the minimum of the Rayleigh quotient. This is really very useful. And you can rewrite the extremal spread in this way if you know the eigenvectors. So if x is corresponding to the largest eigenvalue and z is corresponding to the smallest, then this is just lambda1 minus lambda n in that case. So this extremal spread is just this kind of Rayleigh quotient minus another Rayleigh quotient. And that tells, if you know something, so if you know the vectors, that tells you actually where the edges have to be. So if you look at this quantity, this xu xv minus zu zv, if that thing is positive, that's sort of how much an edge is contributing to this quantity. And if that term is positive, then the edge has to be there in your extremal graph. Otherwise, if you add the edge in, these Rayleigh quotients would strictly increase, and that's a contradiction if you are looking at your extremal graph, right? So in the extremal graph, anytime this quantity is positive, there has to be an edge, and conversely, anytime this is negative, there has to be a non-edge, because otherwise removing it would increase your Rayleigh quotients. Okay, so what that means is that once you know the eigenvectors, your graph is determined. There's some small thing like if this quantity is 0, then maybe you're not sure what's happening, but you can actually show that this quantity is not ever 0 in the extremal graph. Okay, so this idea allows you to say that the extremal graph is a joint. So this is in the original paper. If I split my vertex set up according to the last eigenvector, so I put all the vertices that have positive entry on top and all the vertices that have negative entry on the bottom, then if I look at two vertices, one in each part, and I look at this quantity, xu xv minus zu zv, well, now one of these terms is negative, one of these terms is positive, and I'm subtracting that term. So this is a positive number minus a negative number in that case, and so it's positive. And so what that means is this edge has to appear here. For any choice where one vertex is in the positive part and one vertex is in the negative part, all of those edges have to appear. And so this, whatever the extremal graph is, when you do the vertex partition in this way by the eigenvector, this is complete bipartite between them. So the extremal graph is a join of two graphs, and we're just not sure what happens inside the two parts. So this is in the original paper. In order to say how we extended this result, I need this definition of a threshold graph. So a threshold graph, one way to define it is that you have a function on your vertex set, you assign each vertex a real number, and you make an edge if and only if the sum of the labels is positive, okay? And the breakthrough that we had is that the join of these two graphs, each of the two graphs that you're joining is a threshold graph. And the proof is very easy. Like we did it in a more complicated way at first, but it actually boils down to something quite easy. You just give the threshold function, And then you just note that the sum of the labels is positive if and only if this quantity that we were interested in before is positive. And this only applies to either two vertices that both have positive entry or two vertices that both have negative entry. In between, you already know what's happening. It's complete. And so this absolute value sign, like it goes away. You don't have to worry about these negatives. And so this is nice. Threshold graphs have a lot of nice structure that now you can use when you're trying to say what is your extremal graph. So some of the nice properties that threshold graphs have are there are nested neighborhoods. So what I mean is there's an ordering of the vertices, say from left to right, so that as you go to the right, a vertex. So what am I trying to say? A vertex on the right, their neighborhood is a superset of a vertex on the left. That's what I'm trying to say. You can see that just by this definition, right? If I'm increasing the label of a vertex, it will also have an edge. And what this means is that since you have nested neighborhoods, you can order the vertices in such a way that the eigenvector entries are also monotone. Okay, so you sort of have this partition so that the neighborhoods and the eigenvector entries are monotone. And another thing that happens is that in any threshold graph, there's a partition of the vertex set so that one side induces a clique and one side induces an independent set. And so what this theorem is saying now is that in whatever our extremal graph is, it's the join of two of these threshold graphs. So my graph, I don't know exactly what it looks like. Basically, between these two parts, I don't know what's happening, but I know that my graph looks like this. Okay, and so this is some structure that we can try to use. Okay, so now I'm going to talk about this kind of averaging idea. So what I mean is that if I have my extremal graph, if I move a little bit away from the extremal graph, the spread is not going to increase. And I'm going to see what does that say about my graph, okay? So again, we'll kind of do this thing where we have our extreme eigenvectors. And so the spread of my graph is just the difference of these Rayleigh quotients. And because of the min-max theorem, if I do any perturbation of G, or any graph in general, actually, then the spread of this new graph is at least as big as when I do the Rayleigh quotient with the eigenvectors that I already have, right? So this is true no matter what vectors x and z I choose because of the min-max theorem. And so I can see what happens if I use the eigenvectors corresponding to the extremal graph, right? And so if I do any perturbation of G, then I get this lower bound. And what this means is that this quantity, so basically what this is it's the spread of the extremal graph minus a lower bound for the spread of this perturbed graph. This quantity always has to be positive. Otherwise you didn't start with an extremal graph. So if this is negative, then you've done something to increase the spread. That's what's happening. And so if you do a perturbation of your matrix that's small, this quantity is easy to understand, okay? And so you can see what's happening. You have this quantity that's reasonably easy to understand, and it has to be positive. And this is going to tell you something about your graph structure. And I'll say you can do something slightly more complicated, like I might perturb the eigenvectors as well. So if I perturb these eigenvectors as well, the same thing is happening. Okay, so let's see what this kind of perturbation tells me about my graph. So I'm going to use cloning or averaging. So what I mean is that I might see what happens if I take a vertex and delete it and then add a copy of a different vertex. So that's what I'll call cloning. And I might see what happens if I take a whole set of vertices and just replace them with copies of a single vertex. So that's what I'll call averaging. They're basically the same thing. In order to do this, you want to know which vertex I should clone, right? You have to choose a vertex to clone. And so you should choose the vertex that is helping you the most. So you can kind of ask like, well, how much is each vertex contributing to the spread? And so we can look at this spread in terms of these Rayleigh quotients and just look at all the terms that are using a single vertex u. So let's look at the terms that contain xu, and then it's the same thing for z. So the terms in this Rayleigh quotient that use this eigenvector entry corresponding to u, of course, it's just all the edges. It's corresponding to all the edges that are incident with u. And so you get this twice times xu xv for all v that are adjacent to u. And now this sum of v adjacent to u xv is, by the eigenvector eigenvalue equation, is lambda 1 times xu. And so you get this quantity 2 times lambda 1 times xu squared. And so you can sort of say that like this is, and you can do the same thing with the z vertex as well, right? So kind of this is what's contributing to the spread from a vertex u. And I've removed the factor of 2, like, each edge has 2 endpoints. So in some sense, every edge is contributing to 2 of these terms. But we get this quantity that looks something like this, and you can kind of think about that's like how much u is contributing to the spread. And if I add this up over all u, then I get the spread, right? And so if I delete a vertex v and add a copy of the vertex u, so I have this u v, and they maybe have distinct neighborhoods, right? And what I'm saying is I'm going to delete this and add just another copy of u, so something like this. Then I'm adding another copy of u, so I'm contributing to the spread by this extra amount, but I'm deleting this vertex v, so I'm losing out on my contribution from v. And so this is sort of roughly how the spread is going to change. I say roughly because I'm also going to change the eigenvector. So here before I had some eigenvector with some entries corresponding to u and v, and I'm going to change it to an eigenvector with 2 entries that are the same. And so this changes the eigenvector. So this quantity that I've written here is how much x transpose ax minus z transpose az changes. But when I make this change to my eigenvector, like the norms of the vectors might change a little bit. And so that's why I say this is roughly how much it changes the spread. There's a small error term, okay, but the error term is small. And here u and v are, you can switch the roles of u and v, right? So when I make this change, I better not increase my spread. And if I made the change in the other direction, I also better not increase my spread. And so this quantity that I boxed here, it should be close to 0, right? And so this thing should be approximately 0. And this implies that this quantity, how much each vertex contributes to the spread, this quantity should be the same for all vertices. If they're very different, then I'll clone the one that helps me more, right? That's the idea. And I'll call this the ellipse equation. So this is very helpful. So this tells us a lot about what's happening with our graph. Okay. And I'll do the same thing, but for more vertices. So here with this cloning, what I did was I removed a single vertex and I added a copy of u. And I'll do the same thing for an entire independent set. Okay, so I'll have some independent set with u in it, and I'll change it to so that it has the same neighborhood. The whole independent set has the same neighborhood. So it'll look like this. And now I'm going to impose a condition on the eigenvector entry that the eigenvector entry corresponding to u is the L2 norm of the eigenvector entries in the entire independent set. And this is because, so before, when I said this quantity, the change has to be roughly 0, the roughly happens because the norms of the vectors might change. But if you're only removing one vertex, they don't change very much, okay? If I'm removing an entire independent set, maybe this is like a linear size piece of my graph, then the norm of the vector might change dramatically. And so then this can cause problems. And so I'm going to impose this condition that I have this averaging condition. And so now when I change the eigenvector, the norm of the vector actually doesn't change at all. And I'll say that means u is average on u. And so I'll do this replacement. I replace all the vertices in my independent set by the copy of this one vertex. Because of this average property, the norm of the new vector doesn't change at all. And you can see kind of like, how does the Rayleigh quotient change now? So I'm going to add all these terms that are corresponding to the U vertex, and I'm going to subtract all the terms that were corresponding to the other vertices. And now I just simplify this using the eigenvector eigenvalue equation. And it's exactly what you expect. Like, I'm subtracting how much was contributed by the other vertices, and I'm adding the size of the independent set times how much was contributed by U. And because of this average property, these are actually the same quantity. So what I'm doing is I'm making this change in my graph. I'm kind of replacing an entire independent set by copies of this single vertex. And my Rayleigh quotient is not changing at all. And what that means actually is that what I replaced my graph with, I actually couldn't change the graph at all. That's what it means. But because you're not changing the Rayleigh quotients at all, the spread of your new graph is at least as big as the spread of your old graph. And that means they actually have to be equal, because I was starting with a spread extremal graph. And if you make a big change like this, where I replace one vertex with, or I replace an independent set with copies of this vertex, if I make this change and my eigenvalues don't change at all, that means that this x actually has to be an eigenvector for both of the graphs. And you can work out that this means that, like, my graph actually didn't change. So what I mean is that if I ever can find this vertex U that is average on an independent set, then that independent set has to be already a copy of U. All of the vertices in that independent set already have to be copies of U. And this actually is very strong. Okay, so what this means is that if I look at each of my threshold graphs, there are a limited number of types of vertices. Okay, so what I mean is that I can't have an independent set that has too many types of vertices. I can't have an independent set that has more than 2 types of vertices. So let me try to explain this briefly. So let's say I have a large independent set that I can break into 3 smaller independent sets, so that kind of this independent set on the left has a common neighborhood, this independent set in the middle has a common neighborhood, and this independent set on the right has a common neighborhood. I claim that this can't happen. Okay, the reason is I'll choose a subset here. So let me maybe change the color here. So I'll choose a subset, something like this, and I'll choose a vertex in here U, so that this vertex U is average on, this vertex U satisfies this equation on this blue independent set that I'm choosing. So you have this kind of ordering of the vertices. You have an ordering of the eigenvector entries. If, let's say, these entries are small, these entries are medium, these entries are large, and I have, let's say, linearly many of all of them, then I can sort of choose I can choose in such a way that the L2 average of the vertices I choose is the same as the middle, or roughly the same as the middle. Okay, so up to a small error term, the same as the middle. And then if this happens, then by this averaging argument, this blue independent set that I've circled here actually has to have a common neighbor. So this is a contradiction. So if I have 3 of these types of independent sets, they really are only one type of independent set. And so this reduces the problem to a 10 by 10 problem. So I'll show you how it's a 10 by 10 problem. With slightly more sophisticated averaging, you can actually reduce it to a 7 by 7 problem. So let me explain. We know that we have the join of 2 threshold graphs. And what I'm saying is that in each of these threshold graphs, if I look at the independent set part of the threshold graph, there are only 2 types of vertices, right? So like each of these blobs has a common neighborhood. That's what I'm saying. And now I can just look at the remaining vertices and I can split them up based on which of these independent sets they're adjacent to, right? So I might have a blob of vertices that are adjacent to neither of these 2 independent sets. I might have a blob of vertices that is adjacent to just one of these independent sets. And then I might have a blob of vertices that's adjacent to both of these independent sets. And the same thing is happening on the other side. And I know there's a join between stuff. And so what I'm saying is that because of this averaging argument, whatever the extremal graph is, it really only has 10 types of vertices. And using slightly more sophisticated averaging, you can actually reduce this down to 7. Okay, so I won't say anything about that, but you can get it slightly smaller. And as I said, I thought we were done at this point almost, but it's tricky. So you have to choose the weights, and now you have this 7 by 7 quotient matrix, and basically you want to optimize the weights to maximize the spread, right? And yeah, we thought we would be able to do this by hand, but we couldn't. And so we had to do a computer-assisted proof now. So let me explain how this works. We're going to split into sub-problems. So this is an optimization, like choose these alpha 1 through alpha 7, but I'm going to split into sub-problems depending on which of these are positive and which are 0. Right? If you think about the extremal graph, there's only actually 2 types of vertices, right? So you can think of like 5 of these weights are 0. And so we'll split into a sub-problem for every combination of 0 non-zero weights. So let's do just an example where just alpha 4, alpha 5, and alpha 7 are positive. So I'm saying I only have these vertices. And now I want to choose alpha 4, alpha 5, and alpha 7 to try to maximize the spread, right? And so you can set up an optimization problem. I want to maximize the spread, subject to, now we have several constraints, right? So the first one says that the weights sum up to 1, right? You have to use all the vertices. The second one says that or the second 2 of them say that the eigenvectors are unit vectors, right? That's what it says. And then we can use our discrete ellipse equation, right? So we have all of these constraints for the discrete ellipse equation. We also know that whatever x and z are, they have to satisfy the eigenvector eigenvalue equation. So in this case, we get 6 constraints. And then there's some other technical ones that you know something about, like the order of the order of the eigenvector entries and things, because you have a threshold graph. So there's some other technical ones. And so we want to solve this optimization. We have all these constraints. And basically the idea is that we want to show that this optimization cannot produce the maximum. So our goal, right, is to show that the only sub-problem that produces the maximum is when I only have 2 types of vertices, right? I want to show it's the join of the clique and independent set. And so my goal here is going to be to show that actually, like, I can't produce the optimum. And we're gonna, okay, I have this picture that I already drew beforehand. So to do this, we're going to use something called interval arithmetic. Okay, so this is a technique that's used in I guess numerical analysis, that if you want to, basically I want to rule out that the maximum is anywhere in my search space, right? I have any choice of alpha 4, alpha 5, alpha 7, and I want to rule out all of those choices. So what we're going to do is we're going to create a mesh over our whole search space. So for alpha 4, alpha 5, alpha 7 between 0 and 1. And we're going to show that the optimum can't occur in any of these boxes. Okay, it's impossible to occur in any of these boxes. And to do that, we'll use something called interval arithmetic. So let me give you an example. Let's say I cut up my search space into quarters, and assume there's a 3rd dimension here. So I have alpha 4, alpha 5, alpha 7. I'm going to cut up this search space into quarters. And now let me look at the box that is next to the origin. Well, in this case, alpha 4 is between 0 and 1/4, alpha 5 is between 0 and 1/4, alpha 7 is between 0 and 1/4. And so what we can say is the sum of those quantities is between 0 and 3/4, right? This is what's called interval arithmetic. I am just giving an upper and a lower bound of what my quantity can be. And that means that the maximum cannot occur in this box because this constraint cannot be satisfied in that box, right? And that's what we do for all of these sub-optimization problems, okay? It's not always going to be this easy to rule out rule out one of these boxes, but in every case we can find that one of our constraints is not satisfied. Okay, so that's basically how it works. Let me say a small thing about why this computation is feasible. You know, there's alpha 1 through alpha 7, right? There's 7 variables. In some cases, we had to make the mesh as small as roughly 1 over 2,000 or 1 over 2,500, something like that. And so if you think about first of all, you don't know how small you have to make it in the beginning, right? But if it's 1 over 2,500, if you need to make a mesh that's that small for every variable, that's 2,500 to the 7 boxes, right? And so this becomes computationally infeasible. And so there are a few ways that we sped this up. The first of them is that there are not actually 2 to the 7 subproblems. There's only a small number, because some choices of these alpha i's are the same, right? If just alpha 1 is positive, that's the same as if just alpha 5 is positive. They're isomorphic graphs. So you can reduce the number of subproblems. Because of all the constraints, there are not actually 7 variables. There are only 4 variables. And then you can choose these variables so that the interval arithmetic doesn't hurt you too bad. Like you don't want to divide by 0 and stuff like that. But then the main thing that I want to say is that we use an unequal mesh size. So basically how the proof works is I have this mesh, I cut it up into large boxes, and then I say, oh, well, okay, it was easy to get rid of this box, right? For whatever reason, that box is infeasible, but potentially the other ones are still feasible. And now we cut up each box that still has not been ruled out into smaller boxes, right? So we cut, let's say we were able to rule these out, but not these. So we cut up these boxes into smaller pieces. We do the same thing and we rule out some of these things. Maybe we rule out all of those. And now the ones that are still potential optimizers, then we cut up these boxes smaller. And so at some point we have to get mesh sizes as small as 1 over 2,500, but we don't have to do that for the entire search space. And so this computation, it runs like I want to say it's like 2 hours on a laptop. So we're not using supercomputers or anything. Okay, so let me just say a little bit about how to go back to graphs. When you prove something using graphons, like you can't detect sublinear size things happening. And so you have to make sure that you don't have these exceptional vertices that are actually messing you up. But it's pretty easy because the extremal graph is so structured, you know that your graph looks like this up to a small number of exceptional vertices. Because your graph is so structured, your eigenvectors are also highly stable. Okay, so you can use something called like the Davis-Kahan theorem or other ways, like you understand how your vectors behave here. And all of the vertices have to satisfy the ellipse equation. So that was not, I was just cloning one vertex and removing one vertex, right? So every vertex has to satisfy this ellipse equation. And once you know the vectors, you know when there's an edge and you know when there's a non-edge. And so even these exceptional vertices, though you don't know what's happening to them, you understand their eigenvector entries, and so you can tell what's happening. So that part is pretty straightforward. Okay, so I have 5 minutes left. Okay, so I'll say I only made 2 slides about the bipartite spread conjecture, and one of them is blank, so I'll say 2 minutes about it. If the number of edges is the number of edges in a complete bipartite graph. So let's look at n squared minus 8 edges. Okay, n squared minus 8. If this was n squared minus 9, I would know exactly how to maximize my spread. I would take n squared over 4 minus 9. This should be n squared over 4 minus k squared plus 1. So if it was n squared over 4 minus 9, I would take a complete bipartite graph of sizes n over 2 plus 3 and n over 2 minus 3. Unfortunately, I can't do that, right? So if I want to make a complete bipartite graph or if I want to make a bipartite graph with this many edges, my parts need to be more balanced. So this needs to be n over 2 plus 2, and this needs to be n over 2 minus 2. And now I have to figure out how do I put these n squared over 4 minus 8 edges, right? So it's not going to be a complete bipartite graph, right? There are going to be some missing edges. And so you have to decide, well, is it better to do this on the right, or is it better to take this n over 2 plus 3, n over 2 minus 3, and add an edge there, right? And because this I mean, this graph, it's reasonably easy to calculate at least something about the eigenvalues. There's not too many types of vertices. There's kind of maybe 3 types of vertices in here. And you can get very precise estimates. And the spread of these 2 graphs matches up to like 3 error terms. But in fact, this is the better choice. So that's all I'll say about it. So this if you take the number of edges looks like this for any k that's like up to roughly square root of n, then you get a counterexample. Okay, so that's all I'll say about it. Okay, so I just want to end with just an open problem. The study of the spread fits into a very natural, more general question, is that I'm going to fix a linear combination of my graph eigenvalues. So here it's lambda1 minus lambda n. You can fix any combination you want, and I'm going to fix a family of graphs. And I'm going to ask, well, what is the largest output of the function over this family? So the spread conjecture is saying my family is n-vertex graphs, my linear combination is lambda1 minus lambda n, right? And I just want to say this, I mean, this is an extremely general question. I just want to say some that I think are interesting. So one that I've been thinking a lot about is this spectral Turan problem. So now I just want to maximize lambda1 over the family of f-free graphs, okay? So if you ask this question, when f is a complete graph, you can answer this question, and the answer actually implies Turan's theorem. So there's a spectral Turan's theorem. You can ask this for f is a complete bipartite graph, and the answer implies like the best known result about the Kirkland-Turan theorem. And then you can ask this for other f's, right? So I think this is very interesting. It's like a topic of a whole other talk that I could talk about. But there's a lot of interesting questions in that first bullet point. This one, lambda1 plus lambda n, it's related to, there's this old conjecture of Erdős about making a triangle-free graph bipartite. How many edges do you have to remove to make a triangle-free graph bipartite? And this is sort of a spectral version of that. Like it's kind of related because lambda n tells you something about the max cut, basically. I think this is really interesting. It's harder because this quantity is not, you can't say it as a maximization problem. So like the spread was lambda1 minus lambda n. Lambda1 is the maximum of the Rayleigh quotient. Minus lambda n is actually the maximum of negative the Rayleigh quotient, right? And so doing this perturbation, you get a lower bound on the quantity. Here, the inequalities go in the wrong, they go in opposite directions. Okay, so you kind of don't have that tool. This third one is very interesting. Just maximize lambda3 over n-vertex graphs. And it's not known what the answer is. So it's even the asymptotics. So there's a very natural guess. You take 3 cliques of size n over 3. So you have lambda3 is roughly n over 3. It's not known if that's the best thing. Even like asymptotically, it's not. So yeah, I'm not sure why it's so hard, but it's an interesting question. And then you can kind of do a weighting of this spread. I think that would be interesting. So like if beta is 1, you're just trying to take a complete graph. If beta is 0, you're just trying to take a complete bipartite graph, and you can kind of see what happens in between. And then you can talk about spectral gap, lambda1 minus lambda2 for k regular graphs. There's this old conjecture of Aldous and Phil to maximize this thing, or to minimize this thing. This is, here I want a minimum, actually. And same thing, minimizing lambda1 minus lambda2 over just n-vertex graph. This was a conjecture of Stanich to kind of be an adjacency version of this conjecture of Aldous and Phil. And you can make up whatever linear combination you want, and you'll get a problem. And I think there's a whole world of problems out there that are interesting. Okay, so that's where I want to stop. Thank you very much.
Thank you. Are there any questions?
So I have a question. So isn't it true, Mike, isn't the paper of Nikiforov that shows that this limit always exists if you take like some fixed linear combination of eigenvalues and you divide like the...
So he definitely showed that like if I take lambda k and ask what is the maximum kth largest eigenvalue, then this limit exists. I'm unsure about other linear combinations. You might be right, but I don't.
Oh, okay.